Okay, we're starting.
They're great.
So, last time we finished calculus, so that was a big deal.
Woo!
Yeah! Like I know calculus now. Okay, now we're moving on to part 2 of the class.
Professor, on the next test, you're going to put all the calculus on there still though?
On the next test, it would cover divergence theorem and then the matrices.
Is there no more calculus?
What?
Is there
In the lecture, we're not going to lecture about it anymore, but... So, for those of you who missed calculus, there's something called advanced calculus, so you can continue the journey if you want. It's an option, I'm just throwing it out there. There's some of you are like... There's a course called Advanced Calculus, and you can take that. That'll be fun.
Do you do like examples and how that does?
That's in like more like real analysis. That's more like a graduate course. This is something. So advanced calculus is like you go over calculus, but now you literally prove everything. No one just gives you a theorem and says use a theorem. Now it's like, why does this theorem work? You know, like why does it make sense to do this? Why does the derivative behave this way? You sort of like have to construct everything from scratch.
You gotta be like, it works in some neighborhood.
You sound like you enjoy that class.
Well, yeah. Don't make it like I'm weird for like that. No, that's like things that math majors have to do. It's like just one of the first things. So we're going to talk about linear algebra now. But to be fair, what we're doing is not going to be a linear algebra. They call it that, but we're pretty much going to be doing matrix algebra. Which is kind of like a preview of the highlights of the computational part of linear algebra. So it's good. We're going to skim the surface here. We're only going to be looking at dealing with matrices. Yeah.
Are we basically doing like the first fourth of Math 46 or the first third?
No cut space.
In terms of time, it's like the first third. But in terms of content, maybe it's like the first fifth. Right? It's like, because there are a lot of things that I have to explain the definitions behind it, and when in 346 I actually would prove a lot of the things that I'm not going to prove in this class. I'm just going to tell you, this is it. We do this now. And you're just going to take my word for it. Like in 346 I'd go through and I say, this is why we have to do it this way, and I have to explain and prove it. You know. So, but here we're only going to, it's going to be very computational, so this is going to give a lot of you a chance to boost your grade up. So the third and fourth tests will have mostly matrix algebra, so it will be the easiest of the tests. But you have to remember that very shortly after the final is coming up, so you can't ignore test 1 and 2 just yet. But we're going to talk about matrix algebra, and it's basically going to be a bunch of arithmetic that we're going to be doing right now. So we're going back to the basics. Like, can you add 2 integers? Well, if you can do that, we're okay. Right? Now, if you have trouble with doing that, then I don't know. Okay, we're not going to need to know how to draw surfaces or anything like that. It's just like adding stuff.
So like we're not going any further than like
Okay,
back
so-
substitution basically?
Yeah, so arithmetic, multiplication, adding, subtracting, things like
But no
that.
algebra
Just
though,
knowing-
right?
just knowing
What is
Like we gotta do algebra?
Let's start with the definition.
1 plus 1 equals
So,
3.
in chapter 1 of this section, this is where we're going to talk about matrices and some matrix algebra. I think that's the title of the thing. But really, the entire thing that we're doing is going to be like matrix algebra. So let's start with the definition. What is a matrix? It is also a movie, but in math class.
An array of numbers.
Yeah, it's a rectangular array of numbers. Or in mathematical objects in general, but we will only have real number components in our matrices. Okay, and an array shows you that it's talking about something being arranged in rows and columns. So an example is we have these notations. So like for example, 1, 2, 3, 4 is a matrix. 0 is a matrix. Or pi 3, 7, 0 minus 1, 2, that is also a matrix. There are other notations. Sometimes people write square brackets like this. Right? It's just a different notation. Personally, I would always write like parentheses, but you can write brackets if you want to, because for me it's like too much. Like 1, 2, 3, 4, 5, 6. It's too much. I just like to do this. Yes.
Wait, is that a 0? Like the
This is a
second?
0.
No, the second one.
Yes, just a 0. And it wouldn't matter what number you put in.
So that is one matrices?
Yes.
1 by 1 matrix.
It's a rectangular array of numbers. This one has 2 rows, 2 columns. This one has 1 row, 1 column. This one has 2 rows, 3 columns. This one has 2 rows, 2 columns. Warning. Do not use straight bars. For matrices. So if you look at 1, 2, 3, 4, this is not a matrix, right? This is actually, it means something when you put straight bars. This is referring to the determinant of the matrix. Right? So you can write parentheses or brackets. Do not write straight lines because it means something. Okay? It means something else. Determinant we'll cover in a later chapter. We'll talk about that. But this is just basically a matrix. So you arrange numbers in a rectangle, you have what we call a matrix. The plural of this is matrices. So matrices is the plural of matrix. Matrix is the singular, matrices is the plural. And a lot of what we're doing today will be me talking about just vocabulary, how we call things and what names we give them. So it's a lot of definitions today, and we'll get to more computational stuff in future lectures. But now I just want to introduce it, because I'm not sure if everyone knows what these things are and how they work, so we're going to start from the bottom. So let's start with the matrix. Okay, let me tell you how we're naming things. The numbers in a matrix are called entries usually, but you can talk about them being elements or components. Similar to how we talk about components in a vector definition. We call a horizontal sequence of numbers a row, a vertical sequence of numbers a column. And by the way, it's important, I mean, this lecture you probably don't have to even take notes, as long as you can remember the names of things, you can watch what we're doing. But I'm just sort of introducing the ideas here. Note. Rows are numbered from top to bottom. Starting with 1. Columns are numbered from left to right. Starting also with 1. So I can talk about this matrix here, 1, 2, 3, 4, 5, 6. And if I look at this horizontal sequence, I can say this is the first row, this is row 1. And this is the second row, this is row 2. right? And I can go up top about row 3, row 4, and I can keep going as and 1, 2, 3, 4, 5, 6. I can look at vertical sequences of numbers. These guys are columns. So this is column 1, column 2, column 3. So a lot of things will be described in terms of rows and columns, and I sometimes would number the rows and number the columns. So if I say, look at the second column and do this with it, I need you to be able to locate that and do whatever you have to with it. So these are rows and columns. Just like in functions, we can often name matrices. The convention for naming a matrix is you usually name it with an uppercase letter. Matrices can be named and usually with uppercase letters. So for example, I can say A is the matrix 1, 2, 3, 4. Right? And then every time I say A from then on, you'll know I'm talking about the matrix 1, 2, 3, 4. So similar to a function, we can name it. We usually use uppercase letters. In fact, matrices can represent functions. I'm going to talk about that later, but you just know we can name it. We can also name elements. Using corresponding lowercase letters with subscripts. So for example, I can say, I can write A with a little ij, and that would be, you would consider that to be an element in a matrix, or an entry. The I, the number that's in front, is always the row number. The j, which is the number in the back, is the column number. So for example, in A equals 1, 2, 3, 4, maybe I'll turn a couple more, 5, 6. I can talk about A11, and that would refer to the number that is in the first row, first column, which is 1. What about A23?
First row, second columns of height.
6.
A23?
2, 3, 6.
6,
Okay.
right? That's the guy in the second row, third column.
Okay.
Second row, third column, right? Or A22.
2 to 4.
Right. That means second row, second column, that's this guy. 4, etc.
Wait, don't erase this part. Yeah, you are good.
We can also talk about the size of a matrix. And this is a very important idea. It's a simple idea, but it's very important because there are a lot of operations that we're going to be doing with matrices where the size of the matrix is going to be a very important thing to consider. So the definition is a matrix with n rows and m columns is called, does anyone know what we call it?
N by N? N by M.
N by M matrix. Right, red. N by M. Right? You always list the number of rows first, the number of columns second. It will also follow this notation. That's just a convention we use. Okay? So, for example, 1, 2, 3, 4. and B is 1, 0, minus 1, 2, 3, 9. What is the size of this matrix? It's a 2 by 2 matrix. This one? 2 by 3, right? It has 2 rows, 3 columns. So it's a 2 by 3 matrix. And n by n, notice these are the 2 same letters, matrix, is called a square matrix. So A equals 1, 2, 3, 4 is a square matrix. While matrix B equals 1, 2, 3, 4, 5, 6 is not squared. We're also going to talk in the future about operations we can do in matrices, and some of these operations are only defined for square matrices. Which means if you have a matrix that's not square, that operation would be undefined or impossible. The determinant is an example of such an operation. You can only take determinants of square matrices. Don't know what a determinant is, don't worry about it, we will cover it. But everyone has experience with determinants already. How you compute a cross product is actually taking a determinant. For example, how we find normal vectors is using the parameterization method. You're actually finding a determinant. So we're going to expand on that and talk about determinants in general. So we need to know about square matrices. What else? Let's talk about what did I want to mention? How about diagonal matrix? If it is square, and all its non-zero numbers if any fall on the main diagonal. The main diagonal is the diagonal from top left to bottom right. So an example. Right? Here, all the non-zero numbers fall on the diagonal that goes from the top left to the bottom right. This is an example of a diagonal matrix. Okay. 1, 0, 0, 0, 0, 0, 0, 0. If there's a non-zero number, it lies on the main diagonal. That is also a diagonal matrix. A matrix of all zeros is also a diagonal matrix by this definition. What you care about is that everyone who's not on the diagonal should be all zeros. So these are diagonal matrices. This is another example of a diagonal matrix, but it's important enough to actually have a definition. An n by n matrix with all diagonal entries equal to 1, is called an, you can specify the size if you need to, but you usually don't. We call it an identity matrix. Right. We'll see why it's called the identity matrix pretty soon when we deal with matrix multiplication.
Question.
Yes,
Is the 1 by 1 matrix considered a square?
yes.
How is the second one diagonal?
Because the non-zero numbers in it are on the main diagonal.
But over there it says if it's square. How is the middle one square?
It is square. There are 3 rows,
Oh.
3 columns.
Okay.
So an example here, and the notation for this is I with little n. You can put the little n for emphasis, but usually if you write I, it means identity matrix of the appropriate size. And the appropriate size will be clear from context. So for example, I can talk about I2. That's just the 2 by 2 identity matrix. Notice that on the diagonal, they're all 1s. Or I can talk about I3. This is the 3 by 3 identity matrix. On the diagonal, they're all 1s. You can talk about IN. Right, that just means you have 1s all the way down, 0s everywhere else. Right? And you can say, just call it I if size is clear from context. These guys are called identity matrices. They're a very important kind of matrix.
Oh, sorry. Wait. Sorry.
We now talk about the zero matrix and then start talking about operations.
Okay.
Definition. Now, strictly speaking, in 346, this is not always true, but in 392, it's always true. A zero matrix.
Professor,
Yes.
so the second one and the third one is not a diagonal matrices, right?
It is.
The second one and the third one?
What are we talking about? This one?
Uh-huh.
Yes, they are.
But they have a 0, like, is that,
No, they don't all have to be zeros.
oh, okay.
I said if it has non-zero entries, then it must be on the diagonal. I never said it has to have a non-zero entry. Zero matrix is a matrix with all its entries equal to 0. So example, you can have a 1 by 1 zero matrix, or a 2 by 2 zero matrix, or a 4 by 2 zero matrix. Again, these are all clear from context which size you're talking about, but that's a zero matrix for our purposes. Because we will always do matrices over the real numbers, and the 0 is the 0 for the real numbers. Zero can mean different things in other contexts, but for ours, we'll always be in the context where a zero matrix has all entries 0. So now I'm going to tell you about some operations we can do on matrices, but to sort of motivate the definitions, I think I want to talk about matrices as functions. There's a special class of functions called linear transformations. And matrices can represent these functions. We can think of these as not really going to say more about linear transformations than that. In 346, we go a lot more into what linear transformations are because that's kind of what linear algebra is about. It's about the study of linear transformations on vector spaces, but we're not going to talk about that at all. But I think just kind of illustrating to you how these things fit together will make a lot of things make sense that wouldn't otherwise make sense to you. So here's an example. Consider these functions. And by multidimensional, I'm talking about both the input and output. So in calculus, all the way up until now, when you talk about a function, it's usually the output is always in a one-dimensional space. I don't know if you've ever realized that. So z equals x plus y, right? That's a function, right? Right? Notice that what you're doing is your input is coming from a two-dimensional space and the output is just a number, right? Just one number. Your output is always just going to be one number. When we looked at a vector function, that would more look like what a matrix is. So when we spoke about something like R of u, v, and we said, oh, that's outputs in 3 dimensions. Now we're getting closer to what matrices would normally represent. Notice here I have an input from a 2-dimensional space and the output is in a 3-dimensional space, right? So when you have these kinds of functions, very multidimensional, both the input and the output can have multiple dimensions. If all the components here look like equations of planes that pass through the origin, you obtain what we call a linear transformation, okay? And a matrix can represent such a function. So I'll give you an example. Let's do 3. Define the following functions. Let's say I talk about a function called p of xy. So I'm inputting something from R2. I'm plugging in an x and a y value. And now my output isn't just a single variable, it's actually a vector. So let's say it outputs into something like this. ax plus by, where your a and b are constants, so it could be a 2 and a 7 or whatever, comma cx plus dy. Or I could talk about q of xy. Let's say that goes from 2 dimensions to 2 dimensions as well.
So, Professor, in this case, A, B, C, D are both constant, like all of them?
Yes, everyone except x and y are
X,
constants.
okay.
X and y are my variables. Let's define r of xy. This one I'm going to let output into a 3-dimensional function. I, j, k, l, m, n. Okay. So notice what you can think, how you can think about these functions. P is a function from, say, R2, and the output is also in R2. Q is also a function whose domain is in R2, and the output is in R2. This guy is a function whose input is in R2, but the output is in R3. So it goes from a two-dimensional space to a three-dimensional space. Also notice that the components here look like the equations of a plane that pass through the origin. There's no plus a constant. It's just a constant times x and a constant times y. Okay? So now these guys are the kinds of guys that a matrix can represent. How do we represent it? Well, it really starts out by us being lazy and not wanting to have to write something out like this all the time. So here's how. We kind of want to arrange things so we can write it in shorthand, so we don't have to, right? If I want to go from a 5-dimensional space to a 7-dimensional space, I wouldn't want to have to write out something like this. That's going to be very cumbersome. So let's say I start with p of xy, right, which we know is ax plus by, comma, cx plus dy. So the idea is first we sort of think of these as vertical vectors. That's ax plus by. Put the first component in the top and you list corresponding components going down. So the first component, top row. Second component, second row. And then after a point even that becomes superfluous, because clearly we can see that, oh, let's make sure that the first number happens to be the coefficient of x. The second number in each row happens to be the coefficient of y. So I can sort of ignore the x's and y's. So it turns out when I write this, what I'm actually meaning is I'm considering a function where the coefficients of the x are the guys in the first column. The coefficients of the y's are the guys in the second column. Similarly, Q is going to be very similar. It's also a 2 by 2. But let's look at what R would look like. Right? So if I start with R, ix plus jy, comma, ax plus ly, comma, mx plus ny. And if I try to do the same sort of thing, first component, put it in the top row, second component, put it in the second row, third component, put it in the bottom row. And again, if I want to write that shorthand, to not write the x's and y's, because I kind of know who belongs to x and who belongs to y by their relative positions, this would end up being something like this. Okay. So notice here, this guy, for example, is a 3 by 2 matrix, right? Right, whereas this guy's a 2 by 2 matrix. And hopefully at this point, I mean, it might take you a while to think about it, and we're kind of rushing to copy notes. But do you understand what the importance of the number of rows and columns would represent here? Mm-hmm. When I tell you about the number of rows, what am I actually telling you?
What the output
The dimensions of the output space. If I output into 3 dimensions, I should have 3 rows. The number of columns is going to tell you the dimensions of the input space. Okay? So this here, rows equals dimension of output. Right, well, number of rows. Number of columns equals dimensions of input. So when I look at something like a 3 by 2 matrix, I can just think of that as, oh, this is a linear function that goes from a 2-dimensional space and outputs into a 3-dimensional space. I can think of it as some sort of vector function maybe. But a special kind. It has to be linear. The components have to be linear and pass through the origin. For reasons we will not get into. But now, thinking about these as functions, that will make a lot of other things make sense. So when I tell you a definition, okay, this is definition, this is how you do something, then you're there, oh yeah, that makes sense, because if they're functions, it would have to work out that way. Okay? So now let's talk about some operations on matrices, which now you would know are really representing operations on functions. And so the definitions are going to make a lot of sense. So let's talk about addition and subtraction. Now this is going to feel very natural to do. First, notice that we can that's the first point that I want to bring out. We can only add or subtract matrices that have the same size. Why? Because the size is attached to dimensions. We have to be able to add the same dimensions. That's like me saying, add 2 plus the vector 1 comma 3. That would make no sense to say that. This is a one-dimensional entity. This is a two-dimensional entity. Being able to add them is meaningless, right? So because the sizes of matrices are attached to the dimension of the matrices, it stands to reason that I can only add two things if the dimensions match up. It would not make sense otherwise.
So if we have a 2 by 3 and 3 by 2, we could add them as
We
well?
cannot add them. They're not the same. Right? And again, because of the dimensions are important. Right?
Okay.
So when you talk about a 3 by 2 matrix, say 1, 2, 3, 4, 5, 6, and if you want to add, you don't know if you can do that yet, and you set a 2 by 3, let's do 1, 0, 7, 0, 2, 1. This is a 2 by 3. Notice that here, this guy has input in R2, whereas this guy has input in R3, right? So adding two things is a matter of adding corresponding inputs and getting a corresponding output, but here the input and outputs don't correspond. It's like me asking you to add this to that is like me asking you to add a two-dimensional vector to a three-dimensional vector. It doesn't make sense. It's not mathematically defined. So they have to be exactly the same size. In fact, the number of rows must correspond, right? It has to be a 3 by 2 with a 3 by 2. It cannot be, you can't switch the numbers here. That won't work. It won't make any sense. Okay? So they have to be the same size because the dimensions have to match up. Okay? So we can only add them at the same size, and we do so by adding or subtracting, whichever is called for, corresponding entries. Same way how when you add two vectors, you have to add the corresponding components, right? If I take a vector and add to another vector, I add all the first components together, the second components together, the third components together. So we add matrices by adding corresponding components, or entries. So for example, I can say 1, 2, 3, 4, plus 0, minus 1, 7, 1. And I can obtain another matrix. 1, well, let me actually write it out. 1 plus 0, comma 2 plus minus 1, 3 plus 7, 4 plus 1. So that's 1, 1, 10, 5. And I'm adding corresponding components because when you're adding functions, you add the like terms. You add the x's with the x's and the y's with the y's. That makes sense, right? So it would seem natural to do that just by how things are aesthetically arranged, but the reason why it makes sense to do that is because there are really functions in the background. There are other things that there are other operations that I will do that won't make sense why you do that, but it would make sense after you consider the fact that, oh, these are really functions in the background. Like matrix multiplication. It seems like such a random and crazy thing to students, but that's because they don't realize what it means in the background. So, and I could say something like, I want 1, 2, 3, 4 plus, this is undefined. The dimensions don't matter. So that's easy. Okay. So that's how we can add and subtract. We can talk about also scalar multiplication. Just like how we can multiply vectors by scalars, we can multiply matrices by scalars, because you can even think of matrices as vector functions. Well, how do you think we can multiply a matrix by a scalar?
You multiply every element with this.
Multiply every single entry by the scalar. Same thing with a vector. You multiply a vector by a scalar, you multiply each component of the vector by that scalar. Same thing applies to matrices. For example, if my A is equal to 1, 2, 3, 4, I can talk about what is 3A. Right? I can multiply A by 3, and I can say, oh, that's just going to be 3, 6, 9, 12. Or I can multiply by minus 2A. And so that's going to be minus 2, minus 4, minus 6, minus 8, etc. Right? And that makes sense because they're functions, and I can, to multiply a scalar by them means to multiply every component by it. Let's talk about multiplication. Let's multiply two matrices. 1, 2, 3, 4. 4, 0, 1, 1. How do you think we would do that?
Do the 1 times the row and the other one, and then 2 times that row? I forgot.
1 times this?
Times the whole row.
Okay, and then the 2 would do what?
Multiply by.
And the other one.
Multiply by the bottom one. Doesn't it like turn?
Wait, by the column, right? I remember.
Two
No.
multiplied
Now,
by the one on the
Forget
bottom.
it.
Here's where you might get into trouble by looking at something as being natural. Multiplying corresponding components would be the wrong thing to do. Okay, and the correct thing to do would be to take the 1 times the 4 and add it to the 2 times the 1.
Well,
Yeah. And that is in the top left.
1,
Then you're going to do the 1 times the 0 plus the 2 times the 1.
that's tough.
Then you're going to do the 3 times the 4 plus the 4 times the 1. Then you're going to do the 3 times the 0 plus the 4 times the 1. And as they said, huh? Why does that make sense? Why would I define multiplication in this awfully strange way? Let me tell you why. So you're like, addition, yeah, okay, subtraction, yeah, scalar multiplication, awesome, multiplication, huh? What the hell is going on here, Jawan? Okay, I'm going to tell you what's going on. Consider the functions that I mentioned before. What was my p of xy? That was the ax plus by, comma cx plus dy, right? Yeah. And the last one, the r of x, what was that?
Ix.
I
Plus jy.
J K L N N. Okay. Now here's something I want you to consider. Compute the following. P of r of xy and r of p of xy. You remember what that means? Like if you have f of x and g of x, find f of g of x. We're going way back here.
So in the first one, we're saying that
Professor.
the x value is ix plus jy, and you plugged it in after the a for ax, and then the y value that's plugged in after b is kx plus ly?
I'm not sure what you're saying. Let's talk about this one first. Okay, tell me what you were saying now.
Sure. Well, that first one, that is ax plus by, the x is ix plus jy, and the y is kx plus ly?
And what is this?
I don't know. There's no z listed in the thing,
Uh,
so you don't worry about it.
For this, you put P bracket and put R of xy inside the bracket and then convert it into pxy.
Sure, but what does it mean to plug this in? What is this?
It's that function. The
Yeah,
down-
I know that, but plugging in that means plugging in what?
Input.
It's the input. What am I plugging in here?
Ix plus jy and then kx plus yeah.
Okay, and what is that by our definition?
What is that? Isn't it one two-dimension and then the other one three-dimensional?
Exactly. Does not exist. I can't actually do that. You're asking me to plug in a three-dimensional vector into a two-dimensional space. It's not going to work. I have a z component here. P does not accept a z component as a variable. It can only accept two variables. Here you're asking me to plug in three, undefined.
What do you
In other
mean?
words, what I'm trying to tell you is, if I think of this guy here was what? It was a 3 by 2. This guy here was a 2 by 2. In other words, what I'm saying is, it is impossible to multiply a 2 by 2 by a 3 by 2 in this order. Let's look at the other side. Yeah?
But I don't understand how that corresponds to the other example over there.
When I get to the end, you'll see the things fitting in. Let's do the other direction. What if I said r of p of xy? Okay, so I'm going to plug in the p into the r. So that means I want to take r of what? Ax plus by, comma cx plus dy, right? Which is possible. It's two components and r accepts two components. So what I'm saying is this is going to be like my x value that I'm plugging into the r. And this is going to be like my y value that I'm plugging into the r. So now r looks like I times the x, right? But now this is my x. Plus j times the y, so plus, that's going to be cx plus dy, comma, k times the x plus L times the y, comma, m times the x plus n times the y. Now what is that going to look like? Let's multiply out and collect terms, right? How many x's versus how many y's do I have in the first component? This is a comma. Here I have ai plus cj, right? Look at the y's. I have bi plus dj. Move over here, I'm going to do the same thing. How many x's and how many y's do I have? I have ak plus cl. The y's, I have bk plus dl. Move on to the third component. Let's group the x's and y's. And here I would have am plus cn and bm plus dn. Okay, but that was very cumbersome to write down. Let's translate to the matrix versions. Well, the first line is going to look like this. I'm going to have my R and my P written right beside it. And what did R look like? It was I, J, K, L, M, N. This guy was A, B, C, D. What does the result look like? I'm saying this is equal to this. Now what is the result going to look like?
Professor,
Yes.
wait, can you do the last line one more time? Like, how do you get AI plus?
I'm expanding and then grouping like terms. AIX plus BIJ, BIY, expand the parentheses, plus CJX plus DJY, and then I group the X's and I group the Y's.
Okay.
But what is, if I wanted to translate this as a matrix, what would it look like? All the X components would be written down the first column, right?
Yeah.
So I would have AI plus CJ, then I would have AK plus CL, then I would have AM plus CN. If I write down all the Y's now, I have BI plus DJ. Then I would have BK plus DL. Then I would have BM plus DN. So I end up with this weird sort of formula. Right? Now I don't want to do this, so now it behooves me to figure out, is there a shortcut for going from this to that? And now you can sort of see it. What actually happened was, you can obtain this by taking this row and dot product with that column. And what would you get? You get this component here. If I take the first row and I dot product with the second column, I get this component here. If I take the second row, dot product with the first column, I get this component. Second row, dot product with the second column, I get this component. Third row, dot product with the first column, I get this component. Third row times the second column, I get this component. So I can actually describe this weird formula in terms of dot products. And it's kind of why, going back to Vanita's question in that example, why do I have to multiply this by this and then add it to this times that? I was really taking a dot product. Why was I taking a dot product? It's a shortcut way to remember how to do this. So now I can define matrix multiplication, that weird formula for you. And by the way, this is why it has to work out. So you're going to realize matrix multiplication is not commutative, right? And people might wonder, why is the commutative means you can do it in any order, right? So in real numbers, multiplication is commutative. 2 times 3 is the same as 3 times 2. When it comes to matrices, this is not true, right? Because your matrices are representing functions. You can't always plug in functions in any order and it will work. F of g of x is not always the same as g as f of x, right? So that's why in matrix multiplication, the order is going to matter. You notice when we went the other order, it couldn't work because the dimensions wouldn't match up. But now when we're going this order, suddenly we can get some sort of answer, right? And that's because the dimensions matched up there, right? So the idea here, just to hammer this home a little bit more and then I can write down a definition.
Professor, is that a Bn? And then Bn plus
Bm.
Oh, Bm. Okay.
Yes. As in BME. Or en masse. BMS. So in other words, if we look at R times P, right? Where multiplication here is really composition of functions. That's why it has that weird definition. If you look at RP, remember this was a 2 by 2 matrix. This guy here was a 3 by 2 matrix, right? So basically what that says is P goes from a 2-dimensional space to a 2-dimensional space. So if this is R2 and this is R2, P does this. It takes an element here, outputs an element there. R goes from a 2-dimensional space to a 3-dimensional space. So R would take things from here and would put them in R3. Right? And so now, the reason why RP, that order, makes sense is because the output of P has the right number of dimensions to be the input of R. The other way didn't work, and this was okay. Right? Why didn't the other way work? Because if I went in reverse order, if I started here as R2 and that as R3, R would go do that. But could P do that? The answer is no. Because P cannot take R3 as input. It cannot take a 3-dimensional vector as input. So this is not okay. Right? In other words, we can multiply a 3 by 2 by 2 by 2, but we cannot multiply
2 by 2 by 3.
we cannot multiply a 3 by 2,
2 by 2.
2 by 2 by
3 by
a 3 by 2. And again, why? The dimensions don't match up. These guys are functions. The inputs and the outputs matter. So this weird definition for matrix multiplication is not exactly weird. It's just that it represents a composition of functions. It represents you plugging one function into another function. And that has consequences. It means that the order in which you multiply will matter. It also means that sometimes it cannot be defined. And it also means that you have this sort of strange formula with dot products happening when you're doing matrix multiplication. And the reason for that weird definition is because this is what multiplication means. So when I say matrix multiplication, it's really a composition of two functions. Yes?
Let's say, so P does not take dimension of 3, but if I give it dimension of 1, would that work?
How do you give it a dimension of 1?
So let's say R is a 1 by 2 matrix. So would that be okay? Would the other dimension would just be 0, or this is not allowed as well? I don't know if you know what I'm asking.
But what your question is going to be covered by my definition, so I'm going to...
Okay.
So when I define matrix multiplication, I'm also going to define when it works from when it doesn't, because it might seem like complicated and mysterious when I do it, but I just wanted to illustrate why it's going to make sense when I write it down. Like A, B, and N by M, and be n by p. Then we define the product AB to be the n by p matrix C, where I'm going to give you a formula for the entries now. The Cij, this is lowercase. The Cij entry is equal to the ith row of A dot product. This is a dot product with the jth row of B. Right, so that's we don't have a constraint here. I was very careful in how I wrote it down. So if I'm looking at A, B, this is an n by m, this is an m by p. I want you to take note that these two must be the same to be able to multiply. Why? This is the input dimension, that's the output dimension. So the output dimension of this must be equal to the input dimension of that guy. Right? So if this output is in an m-dimensional space, that guy better take an m-dimensional vector as an input. The outer numbers also give you some information. That gives you the size of the result. So if you multiply an n by m matrix by an m by p matrix, the result needs to be an n by p. Right? And why was that? Let's look at this again, just as an example to illustrate with the p and the q from the previous example. When you take the composition of functions, what are you doing? You're taking an input from here and going all the way to here, right? So the inputs of this is here is r of p. What is the input dimension of this guy? He's going to be the input dimension of p. This has input dimension of p. And what is the output dimension of that guy? It's the output dimension of r. So I need, the result is going to be the input dimension of this guy times with the output dimension of that guy. Yeah.
Should it be the j column? Yeah.
Column, yes. I said that, but I wrote something else. Right, you do this horizontal thing. Right? So why mixed multiplication is this weird and why it only works in a certain order is because of this. It's really functions in the background. And so this is input and out. Did I write it down? And we'll stop there. We'll do some more examples next time or other time.
When are you going to give me all the
There's some more matrix stuff in there.
I'll have a look.
Yeah.